This is going to be a very quick pass over the entire course to give you a sense of the kind of material that we're going to be covering and how it is linked from one section of the course to the other. I start with the electric field E, skipping over the first couple sections which are primarily about calculating the Coulomb force between two charges. I'm going to start with section 21.1, which is about electric field lines, and section 20.3 about calculating the electric field vector. Why do I do this? The reason is that electric and magnetic forces, the forces that we focused on in Physics 2048, are calculated from fields, not the other way around. The force will be found by multiplying the field E by a charge Q. This makes the field E the most important quantity. We'll only use this one single equation for forces in this part of the course. Starting with the Coulomb force, which all textbooks tend to do, makes it hard to learn that the interpretation of a problem must start with finding the best way to calculate a field, not by thinking about how to calculate a force. Field lines are an interesting thing itself in physics. It's a visualization tool that, as I understand it, Faraday came up with. It wasn't quite very popular at the time. The field lines visualize how a charge influences the space around it by producing what's called an electric field. The individual vectors of the electric field are tangent to the lines. These lines are drawn by analogy to what you see when you put iron filings around a magnet. If you know about the modern physics of QED, which explains how photons produce forces, both electric and magnetic, you can sort of imagine that the field lines are something about the way that the virtual photons flow away from a positive charge until they find another charge to push or pull on. The field lines are these solid lines that have arrows showing their sense of direction. They flow away from positive charges, indicating that the electric field points away from a positive charge. The electric field itself is a set of vectors, a vector associated with absolutely every point in space, like you see these two examples here. These sketches show that the field vectors pointing away from that charge are parallel to the radial vector with a direction set by the unit vector r hat. That's how we go about calculating the field vector properties. So you find a point and that field vector must point away, that is in the radial r hat direction, if the charge is positive. There are 5 different ways of calculating an electric field. I mention this only because I want to have you have an idea that the many different ways we found forces in Physics 1 are replaced with the many different ways of finding fields in Physics 2. However, as important as some of these methods are, the most important method is that we can combine solutions from one method with solutions from another method by adding the vector fields that come from each part of a problem. You might use one method for one part and a different method for another part. The most fundamental of these methods is called Gauss's law, which is the first of Maxwell's equations, but we don't get to that until the second chapter that we're going to cover in the course. The electric field is associated with something called a potential, the electric potential. This is the electrical potential energy per unit charge, so it's analogous to the field in the sense that we remove the value of a particular charge that we would use to calculate the potential energy and focus on just the effect produced by the source, the electric field. This is the voltage that can be used to calculate the electric field and then the force that makes a charge move. In particular, this is the bridge point from the first part of the course to the second part of the course where we use the potential, that is the potential energy stored in a battery, to push electric charges around in a direct current circuit. The potential in volts is a measure of how much energy you have in the battery and how that energy can be used to provide a force on electric charges. This little cartoon from the textbook shows a battery on the left and some sort of resistor on the right. It'd be kind of neat if it was a light bulb instead of a little black box resistor thing that you haven't seen yet in the lab. The battery is a source of what's called EMF, which is a strange ancient term for voltage difference. The battery raises charges up to a higher voltage, that is a higher potential energy, and that high potential energy produces an electric field that will push the charges around the circuit. There's a very nice little cartoon of this in our textbook, which shows a couple of girls playing some sort of game with bowling balls and a bunch of posts. The analogy is, instead of the physical work that would be required to lift a bowling ball against the force of gravity, chemical work is done by the battery to raise charges up to the high voltage end of the battery. That voltage difference produces an electric field in the resistor. That electric field provides the force to push charges through the resistor. And then collisions, like with this bowling ball bouncing off of those posts, the collisions produce heat through the process of basically a friction kind of collision process, so that the energy you put in from the battery ends up being dissipated as heat. In principle, the kinetic energy of that ball is constant in this diagram. Now that we have an electric current, we discover that that electric current can produce a magnetic field called B. Magnetic fields are also vectors, but they're a very different kind of vector field in that they go around a wire rather than away from a charge. This picture shows how you use your right hand to visualize how that field is produced. As a current flows along a wire, a magnetic field curls around the wire in the same sense that your right hand curls around the wire. When we go to calculate that, we'll find that those field vectors are perpendicular to a radial vector. The radial vector points away from the wire, which is shown with that little dot. The direction of the field is a right-handed rule cross-product relationship between the vector r and the direction of the current flow. So we'll end up using a vector cross product to calculate the direction of the magnetic field as well as the direction of the magnetic force. Magnetic fields and forces are an extremely unusual thing that unlike anything we've seen in physics up to this point. As this picture shows, the magnetic field vector is again tangent to the field lines, which are circular in this case, going around the wire. The direction is given by a right-hand rule that comes from a vector cross product. As in the case of electric fields, there are several different ways of calculating a magnetic field. We'll only use a couple of those, by the way. But again, if you find that one method works for one kind of problem and a different method works for a different kind of problem, you can combine those just by adding the vector fields to each other. The most fundamental of these methods is one called Ampere's law, which will be the second of Maxwell's equations that we'll learn when we get to chapter 26. There's also a Gauss's law for magnetism, which is worth mentioning when we get there, but not worth talking about, or even hardly talking about here. After we've done all of that, we discover that if we create a magnetic field and that magnetic field changes, for example, we change one of the currents that produces the magnetic field, that process creates an electric potential. This is called Faraday's law, and it's the way in which we generate electricity. It's the fourth of Maxwell's equations and one of the more dramatic ones that one can see in real life. It turns out also to be easy to produce a voltage that varies sinusoidally as a function of time. All you have to do is some very simple things like rotate a coil in the presence of a magnetic field. That results in an alternating voltage that produces an alternating current, what's called an AC circuit, and that will be the fourth topic in the course. I spent a lot of time on AC circuits in this course, much more than the chapter suggests, for two main reasons. Number one, they're the starting point for most of electrical engineering. The better you understand this, the better off you will be. And those of you who are not electrical engineers, if you do anything dynamic in engineering or in physics, AC circuits use the same mathematics as the basic mechanical engineering problem of a suspension system on a car, what's called a driven damped harmonic oscillator, something that's mentioned in our first semester course. There's a little tiny bit about it in the textbook, but when you get to AC circuits, you can see that thing in real life, in the laboratory as well as in our classroom and in our demonstrations in the classroom. That sort of system is fundamental to all sorts of physics and engineering problems. After we've done that, we finish up with a final addition to Maxwell's equations that Maxwell used to predict that light was electromagnetic, that it traveled at a particular speed, a rather dramatic prediction that was confirmed by Heinrich Hertz about 20 years later, showing that you could use that theory to build a device that transmits radio waves. So not only can you study light and optics, you can also study radio waves based on Maxwell's equations. We'll use this as our intro to the idea of properties of waves, such as radio waves, cell phones, TV, whatever, but also light. And we finish up the semester by studying optics, image formation with mirrors and lenses, plus interference and diffraction effects. Those tend to be not very important to most people taking this class, but it is a nice, easy, coast-down way to get out of the semester. So the various pictures here came from our textbook, as I have used in the past.